This video is on section 6.4 notes, double angle and half angle identities. So I've gone ahead and put the double angle and half angle identities up here for you, but they're also on the trig resource sheet. And you can see that there's three different options for the cos double angle identities. And honestly, with this one, I don't really have a preference. It just comes down to whichever one you kind of enjoy using. And then sine and tangent. So I did write a little note to you guys here. It says all of the angles that you can evaluate using these formulas are also just in the unit circle on their own. Does this make evaluating angles with these identities feel pointless to you? Me too. So I already know you're not going to like these because they feel pointless. The one nice thing about this is that if we're going to use a double angle identity to evaluate these, then we know what the answers are going to be. They're going to be values from the unit circle. And so that's kind of nice because when you get done, you'll know if your answer is right or wrong because it will be recognizable or it won't be. All right, so what we're going to do is we're going to find cos of 5 pi thirds, and we're not just going to look at the unit circle to do it. We're going to use a double angle identity to do it. So 5 pi thirds, it's a little bit easier for me to do these problems if I think in terms of degrees when I set them up. So 5 pi thirds is 300. So that means that I'm going to do the double angle identity of 2 times 150 degrees to complete this problem. So this would be 2 cos of 2 times 150 degrees. And 150 degrees is 5 pi over 6. Okay, so 2 times 5 pi over 6, 2 times theta. And it doesn't matter which one of these you do, I'm just going to go ahead and do the first one. So I'm going to do cos squared of 5 pi over 6 minus sine squared of 5 pi over 6. And so if I look at my unit circle, cos is negative root 3 over 2. And sine is 1/2. So negative root 3 times root 3 is just 3. The negatives cancel. And then 2 times 2 is 4. And 1 times 1 is 1, and 2 times 2 is 4. And 3/4 minus 1/4 is 2/4. Which of course is 1/2. And we can check our work. We can say, well, let's look at 5 pi thirds right here. And cos of 5 pi thirds is 1/2. And yippee, we got it right. Okay, next one, we're going to use a double angle identity to find sine of 3 pi halves. 3 pi halves is 270, and half of 270 is 135. So I'm doing sine of 2 times 135. So this would be 135 is 3 pi fourths. Okay, 2 times 3 pi fourths, and so the theta is 3 pi fourths, and so now I'm going to do 2 times sine theta times cos theta. So this is 2 times sine of 3 pi fourths times cos of 3 pi fourths. And then 3 pi fourths, sine is root 2 over 2, and cos is negative root 2 over 2. The 2 in the front I'm going to write as a fraction as well. I'm just going to put it over a 1. And so I can say that the 2 on the top and the 2 on the bottom cancel. I have a negative times a positive, so I'm going to have a negative answer. Root 2 times root 2 is just 2. And then on the bottom I have a 1 times a 2, which is just 2. And so this is negative 1. And so sine of 3 pi halves, if I double check my answer, 3 pi halves, sine is negative 1, and that is the answer I got. So perfect. Okay, and then last 10 pi thirds, this is bigger than the unit circle, 600. So I'm going to do tan of 2 times 300 and 300 is 5 pi thirds. Okay, and so now I'm going to plug this into the formula. There we go. So that is 2 times tan of 5 pi thirds divided by 1 minus tan squared of 5 pi thirds. Okay, and so if I look at 5 pi thirds right here, tan is the y coordinate divided by the x coordinate, and so that's negative root 3 over 2 divided by 1/2, which is just negative root 3. And at this point, I think I said it in a previous video, but at this point you don't have to show all of your work for tangent anymore because we were doing that in chapter 5. So at this point you can just use the ratios that you know work for tangent. You don't have to show every single step for each problem. So 2 times negative root 3 divided by 1 minus negative root 3 squared. And so 2 times negative root 3 would just be negative 2 root 3. And then down here I have 1 minus negative root 3 times negative root 3 is positive, and then root 3 and root 3 is just 3. So that's negative 2 root 3 on the top, 1 minus 3 on the bottom is just negative 2. And then negative 2's cancel, and we are just left with the square root of 3. So if I go back to the original problem, 10 pi thirds, I'm going to have to find something coterminal to that. So 10 thirds minus 2, 4 thirds. So that's coterminal with 4 pi thirds. So tan of 4 pi thirds is negative root 3 over 2 divided by negative 1/2, and so that would be root 3. And so I can confirm that this is correct. So does it feel pointless to use the double angle formula to evaluate something we can use on the unit circle? Like, absolutely. Do I still have to teach you these formulas? Yes, I do. So thank you for bearing with me. I appreciate it. Okay, the next set of identities that we have are the half angle identities. And what I want you to do is put a star next to this one for tan. For tan, we have 3 different options, and the first 2 I want you to never use. Do not use these options. They make your life harder. They make the problem more difficult. We're going to use this one. It makes the problem the easiest. Okay, so we're always going to use that one. We're not going to completely cross them out because I want you to be able to read them in case we end up using them on a proof. But as far as using them to evaluate, we will just not do it. Okay, and then over here we've got sine and cos. You'll notice that we have square roots here with plus or minus in front of them. It doesn't mean we're going to get 2 answers for each problem. It means that we have to consider all students talk constantly. We have to think about what angle is our quadrant, or what quadrant is our angle in, excuse me. We have to think about what quadrant is our angle in, and based on that quadrant, we have to think about, should I use the positive version of the square root or the negative version of the square root when I'm looking for my ratio here, when I'm looking for my answer. So that is why there's a plus minus there, because it could be either of the answers, and we have to do the work to consider what it actually is. Okay, so just like I did with the double angle formulas, I'm going to convert these into degrees because they're easier for me to think about. So 7/8 times 180, it's 157.5 degrees. And I'm going to write this off to the side. 157.5 degrees is in quadrant 2. All students talk constantly. The S is in quadrant 2. That means that sine is positive, but cos is not. So that means we're going to get a negative answer for this when we use the formula that has a plus or a minus in the front. We're going to use the minus version. Okay, 157.5, I'm going to double this. I'm going to multiply it by 2 because I want to see what angle was divided in half to get this. So 315 is divided in half. So I'm going to say cos of 315 divided by 2 is how they got this angle, and 315 is 7 pi fourths. Okay, so now I'm going to go ahead and use the cos formula. I'm going to say the negative version of the square root, 1 plus cos of alpha, 7 pi fourths. So I'm using just the angle that is being divided in half. 315 is being divided in half. 1 plus cos of 7 pi fourths divided by 2. Okay, cos of 7 pi fourths is root 2 over 2. All right, so I have 1 plus root 2 over 2 divided by 2. Okay, now so I can add these two fractions together. I'm going to take the 1 and I'm going to rewrite this 1 as 2 over 2. Okay, so at this point, I now have, oh, and I have a negative in front of my square root. I have 2 plus root 2 over a common denominator of 2. And this is being divided by the 2 on the bottom, and I'm going to write this as a fraction. I'm just going to put it over 1. Okay, and now what I can do is I can say keep it, change it, flip it, or I can keep the fraction and multiply by the reciprocal. However you want to think of it is fine. So I'm going to go ahead and write that work down. Okay, so from here I went up here. All right. Now, from here, I'm just going to multiply these fractions straight across. So 2 plus root 2 is being multiplied by 1. 2 is being multiplied by 2. So 2 plus root 2, and then on the bottom, I have 4. Okay, now when you have a fraction that is being square rooted, that square root really applies to the top and it applies to the bottom. So what we have is negative square root of 2 plus root 2 over square root of 4. That's what we actually have. And luckily for us, the square root of 4 is just 2. So this is negative square root 2 plus root 2 over 2. And this is our final answer. Now, just like we had with the sum and difference formula, and we had repetitive answers because the answers are coming from numbers that are being plugged in from the unit circle, and those numbers are repetitive. These are repetitive as well, which means we just did a process that you're going to be repeating, and it's going to feel familiar to this. So this looked a little crazy, but they're all going to kind of look like that. All right. So let's go ahead and we'll double check this and we'll make sure we got it right. So I'm going to plug this in terms of radians. I'm going to make sure my calculator is in radians. And then I'm going to hit cos of 7 pi eighths. There we go. We have a negative decimal. Now I'm going to type this fraction in. So alpha y equals, so I can have a fraction. On the top, I'm going to have negative, and I'm going to have a big square root sign. 2 plus the square root of 2 divided by 2, and I get the same decimal, so I know I did it correctly. Okay, let's try the next one. So sine 5/12, gonna find the degree measure of that, 75 degrees. Okay, 75 degrees is in quadrant 1. And in quadrant 1, all of the angles, all students taught constantly, all of the angles, or sorry, all of the ratios are positive, which means that sine is going to be positive. And so I'm going to be doing sine, double of 75 is 150. I'm going to be doing sine of 150 divided in half for my half angle formula. And 150 is 5 pi 6. Okay, So I'm going to do the positive version of 1 minus cos 5 pi 6 over 2. 1 minus cos of 5 pi 6 is negative root 3 over 2 over 2. And so here I have a minus minus is going to make a plus. And then this 1, just like we did up here, we need to combine these two fractions. And so we're going to get a common denominator by taking the 1 and writing it as 2 over 2. Okay, so, and I have the positive version of the radical. And so I'm going to have 2 plus root 3 over 2, and this is being divided by 2. I'm going to write it as 2 over 1. Okay, positive version of my answer. So now I can keep it, change it, flip it, or I can multiply by the reciprocal. So 2 plus root 3 over 2 times 1/2. 2 plus root 3 over 4. And I know I can split the radical, have a radical on top, have a radical on bottom. And so my final answer is 2 plus the square root of 3 divided by 2. Well, square root of 2 plus square root 3 divided by 2. And if I wanted to check my answer, I could plug that in and find the decimal and plug this in and find the decimal and just make sure that they're the same. And I know that it's the positive version because I was in quadrant 1 and sine is positive in quadrant 1. All right, let's go ahead and do tangent. So tangent of 5 pi 8ths, 5 eighths, 112.5. 112 is in quadrant 2. All students taught constantly. Sine is the only one that's positive in quadrant 2. We know that tan is going to be negative. If we look up here, though, I only have to choose the sign of my answer if I use the first formula, and I'm never going to use that formula because I'm always going to use this one. I'm going to use this one because it's easier. So don't test me on this. Always just use the easier one. All right, 112. I'm going to double that. It's 225 being divided by 2. So tan of 225 over 2. 225 is 5 pi 4ths. Okay, so we have to do, the formula is 1 minus cos alpha over sine alpha. Okay, and so when I do this, I get 1 minus cos alpha is negative root 2 over 2. Sine alpha is also negative root 2 over 2. Okay, so the 1 I'm going to rewrite as 2 over 2. I know that minus minus makes a plus. Okay, so in the numerator, I have 2 plus root 2 over the common denominator. And then in the denominator, down here, I have negative root 2 over 2. And so now I can do keep it, change it, flip it. And these 2's can cancel out. Okay, and what I'm going to do, you can deal with the negative however you want. I went ahead and I took this negative and I just moved it to the top of the fraction because that's what mathematicians typically do. So I'm going to take this negative and I'm going to move it up here to the front. Okay, and when I move it to the top of the fraction, it's going to distribute. Okay, you won't have to do this on every single problem. I happened to choose one that was kind of gross. So for the top of the fraction, I have a -2 minus a square root 2. And then I have a square root 2 on the bottom. And then we have to rationalize the bottom. And we're going to do that by multiplying by root 2 over root 2. Okay. So in the denominator, root 2 times root 2 is just 2. Okay. In the numerator, we have to distribute this. -2 times the square root of 2 is -2 square root 2. You just write them next to each other. And then root 2 times root 2 is -2. So root 2 times root 2 is the square root of 4, which is 2. Now, both of these are divisible by 2. And so we'll make sure that we just divide all of these numbers by 2. We can't touch the radical. We're not simplifying a radical. But everything else is divisible by 2. So 2 divided by 2 is 1. 2 divided by 2 is 1. 2 divided by 2 is 1. And so my final answer is -root 2 minus 1. Most people, most mathematicians, would probably say -1 minus root 2, but honestly, it doesn't really matter. Okay, now I'm going to show you why you should not use those other tangent formulas. And I'm not going to make you do the math to do it. I'm just going to show you why not. So if you had used the first formula, then this is how you would have started the problem. You would have had it underneath the square root, and you would have done this, and you would have ended up with this mess. Okay, and then you would have had a radical in the denominator, but also under a big radical here. And then when you went to rationalize it, it gets very messy. And it ends up with this terrible answer that is equivalent to the answer we got, but just looks really bad. So please don't use that version, okay? And then here is the middle version for that problem that we just did. If you do this, it just has you put the more complicated part in the denominator, which means that when you rationalize it, you're rationalizing it in a more complicated way. So it works out pretty much the same all the way through until you get here. Then this part is nice because dealing with the negative was nice, but to fix the denominator, to rationalize the denominator, instead of just multiplying by the radical, which is what we did, we just multiplied by the radical. Instead of doing that, you have to multiply by the conjugate, and then you have to FOIL, and anyway, you get the same answer in the end, but it's hard work. It's more work. And so, like I said, just use the third formula for tan, and your life will be easier. Okay? Perfect. All right, next page. All right, on this page, we're going to find the exact value of sine of alpha over 2, given that sine alpha is 3 over 5. So we're not using a value from the unit circle. We're imagining that we've drawn a triangle. And that triangle is for an alpha value of pi halves to pi. And so this triangle would have been drawn in quadrant 2. And if you recall, when we went over problems like this in a previous section, there's two different ways you can do it. You can actually draw the triangle in quadrant 2 and label the opposite side as 3, the hypotenuse is 5, and then go through, and if we're doing sine of alpha divided by 2, then we're going to need to know the ratio for cos of alpha. So then we would need to draw our triangle and find cos. That's one option. Or if we wanted to do a Pythagorean identity, we could do sine squared plus cos squared and do that to find cos. And so that's what I'm going to do. I don't feel like drawing a triangle, and so I'm going to go ahead and do sine squared plus cos squared to find what cos alpha is. And so if we're in quadrant 2, all students talk constantly, then I know that in quadrant 2 only sine is positive, and so whatever ratio I get for cos is going to end up being negative. So I know that from the beginning. So let me go ahead and just do that Pythagorean identity. Sine squared plus cos squared equals 1. Sine is 3/5. Cos is what I'm solving for. And so 3/5 times 3/5 is 9/25. And so I'll go ahead and subtract the 9/25 to the other side. And to be able to subtract these fractions, I'll go ahead and write the 1 as 25/25. And so cos squared is 16/25, which means that cos is plus or minus 4/5, right? Because you're square rooting, plus or minus. And then because we're in quadrant 2, it's definitely going to be the minus version. So cos alpha is -4/5. Okay. So now I can go through and actually find what sine of alpha divided by 2 is, and we're going to treat this now like one of those half angle problems. So I know that alpha is between pi halves and pi, but I need to know what alpha over 2 is between so I can know if the ratio for sine should be positive or negative. And that's because, if you recall, back here in our formula, we have to make the determination based on where that angle is, based on where alpha over 2 is. We have to determine if that ratio should be positive or negative. So if I know that alpha is between pi halves and pi, then alpha over 2, I'll just go through and I'm just going to divide by 2. Then we know that alpha over 2 is between pi halves, and pi halves divided by 2 would be pi fourths. So alpha over 2 is between pi fourths and pi halves. Oops, that's a 2, pi halves, which means that alpha over 2 is in quadrant 1. And we know if we look at all students talk constantly that in quadrant 1, every single ratio is positive. And so we're going to use the positive version of cos. Sorry, not the positive version of cos. We're going to be evaluating for sine, so we're going to use the positive version of that when we go through and do this problem. Okay, so I'm going to go ahead and write this down with the formula now. So I'm going to do the positive version, square root 1 minus cos alpha, which is -4/5, over 2. The 1 I can rewrite as 5/5. Okay. Minus a negative I can rewrite as a plus. Okay. So 5/5 plus 4/5 is 9/5 divided by 2. I'll make that a 2 over a 1. Okay, and so I can keep it, change it, flip it, or I can take the 9/5 and multiply by the reciprocal. So this is the square root of 9/10. And so that means that I'm going to get square root 9 over square root 10, which is 3 over square root 10. So sine of alpha over 2 is 3 over square root 10. And if I wanted to rationalize that, and I typically do, then I'll multiply by root 10 over root 10. And I get 3 root 10 over 10. All right, so if you have to evaluate using double or half angle formulas, that's how you do it. Next, we're going to go ahead and talk about some proofs. So our strategy here is to, just similar to the sum and difference formulas that we talked about in the last video, is that if we have a double or half angle identity, we're going to sub that out first. And then we'll go through and use some of our other strategies. So if we look at this first problem, this could be somewhat confusing because if I looked at this, I'd say left side, right side, the right side looks more complicated. However, the left side is where we have a double angle identity kind of hidden. And so I'm going to end up working with the left side first. And what you'll see is that after I sub out something for this double angle identity that has a little bit more going on with it, because you can see there's a 3 there. Once I sub it out, you can see that it actually was secretly more complicated than the right side. It just wasn't apparent from the get-go. So what I'm going to do first is I'm going to take this 3x and I'm going to write this as sine of x plus 2x. So it's a sum identity, but it also has a double angle identity. And that's what makes this a complicated problem. So it's kind of got both things going on. It's got something from section 6.3 and then also what we're doing right now with section 6.4. All right, I know from section 6.3 that when I add two angles together with sine, that I end up getting sine of the first angle, cos of the second angle, plus cos of the first angle, sine of the second angle. And so I'm just going to go ahead and write that down. But I'm using the sum formula to write that. So I've got sine of x cos 2x plus cos x sine 2x, and then that's going to equal just the right side. Okay. Now for cos 2x and sine 2x, I have to look at my double angle identities, and for cos 2x, I have options. So cos 2x we know is cos squared minus sine squared, or 2 cos squared minus 1, or 1 minus 2 sine squared. I decided to use the first one because it reminds me the most of the right side. Cos squared minus sine squared, cos squared minus sine squared. So I'm going to go ahead and use that one. So I've got sine, and then it's being multiplied by the cos double angle identity. So cos squared minus sine squared. And then cos is being multiplied by the sine double angle identity. And this one we don't have options, we just have to write the one thing down. So 2 sine x cos x. Okay, and when I did this problem on my own, I didn't really feel good about it at this point. So I just trusted the process, and I went ahead and I just distributed sine and distributed cos to see what was happening from here. So I get sine cos squared, and then I get minus sine to the third. And then here I get 2 sine cos squared. Okay, and then here's where you can see that you have 3 of something, right? We can see 3 cos squareds over here. You have 1 sine x cos squared and 2 sine x cos squareds, and together these give you 3 sine x cos squareds. And from here, we just need to do what they did on the right side and factor out a sine. So if I take the sine out from here, then we'll have 3 cos squared. If I take 1 sine out from here, then I'll have a sine squared. and they're the same. All right. Now, I included this next problem on here because I wanted to remind you that no strategy is helpful 100% of the time. So the strategy that I just said was that if you see a double angle formula, sub it out. Put the whatever the double angle thing is, put that in for it. Well, this problem is the opposite. This problem is one where you want to actually get the left side in terms of double angle formulas, because you have a double angle formula on the left side and you have a double angle identity, you have a double angle identity on the left side and a double angle identity on the right side. And so when you look and you choose a side to work with and manipulate, you don't want to get rid of the double angle identity because your final answer needs to be one too. So if I look over here, I can see cos of 2 times the angle, and this equals 1 over tan, right? So I'm thinking, oh, I should probably get the bottom to be sine of 2 times the angle, because the right side is basically cotangent, right? If it's cos over sine, then it would basically be cotangent. That's kind of what I was thinking. So when I looked at the bottom, I was trying to figure out if there was a way for just everything in this problem to be a double angle identity. And so when I looked, I saw that 2 sine x cos x is actually the sine double angle identity. So what we're going to do is we're going to start off by taking what's in the denominator of the left side and actually turning it into a double angle identity instead of subbing this one out. And so here we're going directly against the strategy that I just taught in the previous problem. And so like I said, no strategy is helpful 100% of the time. I would not normally say to do this, but it actually helps in this problem. Okay, so here we have cos of an angle over sine of an angle. That gives us cotangent of that angle. And cotangent of an angle is the same thing as 1 over tan of that angle. So this proof happens to be very easy if you do not use the strategy. All right, the next problem uses one of our half angle identities. So it says to use a half angle identity for tan and then a half angle identity for cotangent, and we don't have those. So we're going to have to use tan, and then we're going to have to do 1 over tan to equal cosecant on the right. So I know, first of all, that I'm going to have to not have cotangent here. So I'm going to start with tan of a half angle identity plus 1 over tan of a half angle identity equals 2 cosecant. Okay. And then if I look at the tan half angle identities, I can manipulate this a little bit. I can choose the ones that are easier to work with. So I like sine being in the denominator because that's just a single term in the denominator. I don't want to deal with square roots in this problem. And then also when I'm thinking about the final answer that I'm going to have cosecants. And cosecant is 1 over sine. So that tells me, you know, maybe sine in the denominator is a good thing. Square roots with cos on the inside, not so helpful. So I'm going to go ahead and use this one for the first tangent. So I'm going to do 1 minus cos over sine. And if you notice the relationship between the angles, this is a half angle for tan, but for cos and for sine, it's just the regular angle. Okay. Then for this other one, I know that I'm going to be putting the half angle identity on the bottom of a fraction, which means I'm going to do keep it, change it, flip it. I want something that I can add to this once it's flipped. So I don't want to use the same fraction because if I flip it, it's going to be sine over 1 minus cos, and that's not very helpful. However, if I use this one, then when I do keep it, change it, flip it, this is going to become flipped, and it's going to have a 1 plus cos in the numerator and a sign in the denominator, and a sign in the denominator is helpful. So I'm going to use that second one, 1 over sine over 1 plus cos. So remember what I said when we got to these half angle identities. We put a star next to this one because when we're evaluating, we only use this one. But the reason we didn't cross out the other ones is because when we do proofs, we might want them. That's why we're not ignoring them completely. So in this proof, it is beneficial to use both of these. Okay, so I have the half angle for tan and 1 divided by the half angle for tan over here. Okay, so for the first fraction, I'm just going to copy it down. For the second fraction, I'm going to keep the 1. I'm going to change it to a multiplication problem, and then I'm going to multiply by the reciprocal. So I have 1 times 1 plus cos over sine. So these two fractions can now be combined together. They have a common denominator of sine. And they have a numerator of 1 minus cos plus 1 plus cos. And if we look here, the coses cancel, and we get 2 over sine. Okay, so 2 over sine, you can think of it as 2 is being multiplied by 1 over sine x. That's how you can think of this. 2 is being multiplied by 1 over sine x. And we know that 1 over sine x is just cosecant. So this is really 2 cosecant x equals 2 cosecant x. We just proved it. All right, one last proof for us. Okay, so it says we're going to do sine squared times cos squared of these half angles equals sine squared over 4. And so I'm going to use the strategy of subbing out the half angle identity first, and I happen to have 2 of them. So I'm going to look at the half angle identity for sine. Let me hold this down here. Okay, half angle identity for sine, and the plus minus doesn't matter because I'm going to be squaring it. So for sine, there's sine squared, and then this one is for cos squared. Okay, sine of x divided by 2 squared. Cos of x divided by 2 squared equals the right side. Okay. So when you square a square root, they just cancel out. So the square root and the squared cancel. The square root and the squared cancel. And I get 1 minus cos over 2 times 1 plus cos over 2. And so now I need to multiply the numerators together. And when I do, when I multiply 1 minus cos times 1 plus cos, I need to FOIL them. And so I'm going to go ahead and FOIL it off to the side over here. So 1 times 1 is 1. 1 times positive cos is positive cos. Negative cos times 1 is negative cos. and negative cos times positive cos is negative cos squared. And so the positive cos and the negative cos cancel out, and I'm left with 1 minus cos squared. So that is what ends up in the numerator. So I have 1 minus cos squared in the numerator. In the denominator, I have 2 times 2 is 4. Okay? And then I've got some squareds here that tells me to think about my Pythagorean identities. And 1 minus cos squared is the Pythagorean identity. Well, sine squared plus cos squared equals 1 is the normal identity. But this is an alternate form. And we know that 1 minus cos squared is the same as sine squared. So we have sine squared over 4 equals sine squared over 4. And so that's done.